This video is the central limit theorem. If you have not done so already, please watch the central limit theorem with bunnies and dragons video that is located just prior to this video on Blackboard. So hopefully you watched the video with the bunnies and dragons and you were introduced to the central limit theorem. The idea of the central limit theorem is this. You take some quantity that isn't necessarily normally distributed, such as the dragon wingspans from the video. Dragon wingspans are known to be bimodal, so it's not a normal distribution. However, if you take a large sample of size n, say where n equals 1,000, so samples of 1,000 dragons, and you find the average wingspan in that sample, so you take all the wingspans in that sample and you find the average and record that average, and then you take another sample of 1,000 and you find all their wingspans and take that average, and then take another sample and find the average wingspan or the mean wingspan of each of those samples. If you take the records of all those means, all those averages, and use them to create a histogram, it's going to be symmetric and bell-shaped. And that is regardless of whether the original distribution was symmetric or not. But the sample averages, the sample means of your samples will be a normal distribution, which is really cool that that's how things work out. So if it was already a normal distribution, like the bunnies, the weights of the bunnies from the video, those were already a normal distribution. But when you took samples and he weighed those samples and found the sample weight of each of those samples, those averages of the samples came out to again be a normal distribution. So that's what the central limit theorem is about. It's whether it is or it is not a normal distribution. If you take a sample from that population, no matter what shape that population is as far as the distribution goes, the sample averages will be a normal distribution if the sample size is large enough. So how large is large enough? We're going to say large is a sample size that is more than 30. So if it's a sample size that's less than 30 and the distribution was already normal, then it's fine. The sample averages will also be normal. But if it is not a normal distribution to begin with, let's say it's skewed left or skewed right, or it's bimodal, in that case you will need a sample size bigger than 30. And if you have a sample size bigger than 30, then the sample means will form a normal distribution. Now, the mean of this distribution, of the sampling distribution, will be the same thing as the population mean. Check out the notation for the mean of a sampling distribution. It's mu with a subscript x bar. So that kind of makes sense. The mean of the sample averages, because remember x bar is sample, the sample average, the sample mean. The mean of the sample means is kind of what that stands for. And it is the same thing as the population mean. So if the population mean is 15, then if you take a bunch of samples and you find the mean of each of those samples, then the mean of the sample means will also be 15. Now let's talk about the standard deviation of the sampling distribution, the distribution of the sample means. It is going to be the same as the population standard deviation divided by the square root of whatever the sample size is. So we call this standard error. So the standard deviation of the sample means, say standard deviation symbol of the sample means, x bar, instead of calling it the standard deviations of the sample means, we call it standard error. And it is the population standard deviation divided by square root of n. You definitely need to know this formula. So what this means is everything we know about the normal distribution applies to the distribution of the sample means as well, as long as the sample size is large enough or the distribution was already normal to begin with. Okay, so let's just work some examples and I'll show you what I'm talking about. Okay, so let's look at this problem here. The mean of college students in 2008 was mu equals 25 years with a standard deviation of 6.8. A simple random sample of 64 students is drawn. What is the probability that the average age of students in the sample is greater than 26? So this one is different than what we're used to because we're finding the probability of not the entire population, but the probability that the average age of the students in the sample, that the sample mean is greater than 26. Okay, so we still can use normal CDF, but we need to use rules for the central limit theorem because we're no longer talking about the distribution of just college students. We're now talking about the distribution of samples of college students. So we can start by drawing our normal distribution. It doesn't say that it is a normal distribution, but because our sample size is bigger than 30, we know that the distribution of the sample means will be a normal distribution. Now, the mean of the sample means is the same as the population mean, which is 25. And the standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size, 64. Now you can go and you can calculate what that is if you want to. I just usually leave it as 6.8 over square root of 64. So now, what is the probability that the average age of students in the sample is greater than 26? So 26, I'm going to say, is about right here. Greater than would be this way. Okay? So we're going to do normal CDF. Our lower boundary is 26. Our upper boundary is infinity, so 1e, 99. The mean is 25 because the mean of the sampling distribution, the mean of the sample means, is the same as the population mean. Now the standard deviation, that's what's going to change. That's the one thing that's going to change here. So it's not 6.8, it's 6.8 over the square root of 64. And you can put that in the calculator just like that. So let me show you. So second vars, 2 for normal distribution. The left boundary is 26. The upper boundary is infinity, so 1 e second comma 99. The mean is 25, and the standard deviation is 6.8 divided by the square root. Now square root is second x squared of 64. You can close the parentheses if you want, but you don't have to. But you see that I typed it in just like that. I didn't calculate what that was. I'm going to let the calculator do that for me. Paste. And we get 0.1197. So the probability that the average age of students in the sample is greater than 26 is 0.1197, or about 11.97%. All right. So why don't you pause the video and you try example 2. Let me go ahead and read it to you. It says if the mean weight of a bull is 1135 pounds with a standard deviation of 97, would it be unusual for the mean weight of 100 head of cattle to be less than 1100 pounds? Now, first let me state that a sample is taken. It's a sample of 100 cows have been taken, and we want to know if it's unusual for the mean weight of 100 cows or 100 head of cattle to be less than 1100. Now, unusual, let me remind you, we consider something unusual if the probability is less than 0.05. So basically, that is what you want to look for. You want to look to see if it's less than 0.05. So why don't you go ahead and pause the video and attempt this one. Okay, so we did normal CDF, negative infinity to 1100. Mean is 1135. The standard deviation we put in is 97 over the square root of 100. Now, I put that in the calculator and I got 1.5417, etc., e negative 4. So 1.5417 e negative 4. So So remember, this is in scientific notation. That means we're going to move the decimal back 4 places to the left. And everywhere there wasn't a number, we put 0. So our new number is 0.00015. But we want to round to 4 decimal places. The 1 looks at the 5, and the 5 tells the 1 to become a 2. So 0.0002. That is less than 0.05. So is it unusual? Yes, it is. Okay, so why don't you attempt example 3, pause the video, and then come back and we will go over the answers. Okay, so for the first one, we're going from 26.5 greater than that, so normal CDF 26.5, infinity 27, and then the standard error 3 over square root of 60, and we got 0.9016. Between 26 and 26.8, we did normal CDF 26, 26.8, 27, 3 over square root of 60, and we got 0.2979. And last, would it be unusual if the average were less than 26? So we did normal CDF, negative infinity, 26, 27, 3 over square root of 60, and got 0.0049. That is less than 0.05, so yes, it would be unusual. All right. So one more example, example 4, NYC rent. Why don't you go through these and try to answer them, and then come back and I'll have the answers. So go ahead and hit pause, and when you come back, the answers will be up. Okay, so for the real estate group, NY reports that the mean monthly rent for a 1-bedroom apartment without a doorman in Manhattan is $26.31. Assume the standard deviation is 500. A real estate firm samples 100 apartments. What's the probability that the sample mean is greater than 2,700? So that is 2,700 to infinity, 2631. Use the standard error, 500 over square root of 100, because we're doing this for a sample of 100 apartments, and that would be 0.0838. What is the probability that the sample mean rent is between 2,500 and 2,600? So normal CDF, 2,500, 2,600, 2631, 500 over square root of 100 is 0.2632. Find the 60th percentile. That's going backwards. That's defining the boundary that separates the lower 60% from the upper 40%. That would be I and V norm, 0.60, 2631, 500 over square root of 100, which is $2,643.67. So 60% of the apartments in the sample are less than 2643.67, and 40% are more than that. Would it be unusual if the sample mean were greater than 2,800? So normal CDF, 2,800 to infinity, 2631, 500 over square root of 100 is the sample, the sample error, the standard error, and we got 3.62 e to the negative 4, which we would convert to regular format, which would be 0.000362 if you move the decimal 4 places to the left, which would round to 0.0004, which is less than 5%, so yes, it would be unusual. Do you think it would be unusual for an individual apartment? So no longer the mean of the 100 apartments, we just are talking about one apartment to have a rent greater than 2,800. So it's the normal CDF, 2,800 to infinity, 2631, but we're not doing 500 over the square root of 100 because we don't have a sample of 100 apartments. We just have one apartment. So we could just do 500 over square root of 1 if we wanted, which is just 500. And we get 0.3677, which is not greater than 5% or 0.05, so no, it is not unusual. So if we're talking about an individual apartment, we no longer have to use central, well, I guess we are using central limit theorem, but it's over the square root of 1 instead of the square root of the sample size because it's just 1. Okay, so 0.3677. All right, so that's all for central limit theorem. Let me know if you have questions.